I want to work through a few practice problems because I know time value of money is a concept a lot of people have trouble with. Even finance majors have difficulty with it. And the thing that helps, I think, is to practice. So if you go to the practice quiz for exam 1, you'll find a fair number of practice problems relating to time value of money. But I wanted to work through a few more, and I've provided this Word document without any answers on it for you to download and just try the problems yourself first. But then I'll also provide the document with the answers, and then of course this lecture. So let's say that you bought a house 5 years ago for $300,000. That's an investment. It doesn't matter if I'm talking about buying a house, buying shares of stock, shares of a mutual fund, investing in a corporate bond, whatever. Anything that you purchase at some point with the hopes of selling it at a future point for more money than you paid for it is an investment. Of course, it doesn't always work out that you can sell it for more than you paid for it. But in my example today, it did work out. We sold it 5 years later for $387,000. Now, even though I explicitly wrote the word today, and today is the present, that does not make this $387,000 a present value. The $387,000 relative to the $300,000 purchase price is a future value. So the $300,000 is a present value, the $387,000 is a future value. And ignoring taxes, any interest on the mortgage loan that we had to pay, any upkeep we did to get the house into a sellable condition, we're going to ignore all of that. We're just going to look at the price we paid and the price we sold it for. I want to know what annual rate of return you earned. We would calculate that using the future value. Well, actually, let me backtrack that a little bit. You now have to decide what equation to use. Is this or basically what interest factor table to use? Is this a single sum or an annuity? It's a single sum because I just paid this, and so one payment occurred and I received this. So I invested this single sum. It was not an annuity. And then I need to decide, is it a future value or present value of a single sum question? And honestly, because I have both the present value and the future value, I actually can use either the present value or the future value of a single sum interest factor table. I just have a preference for the future value of a single sum, just because the formula is so easy. It's just slightly easier than the present value of a single sum formula. So again, the future value of a single sum is equal to the present value of a single sum, but since I'm using the interest factor tables, I would multiply by, actually I'm going to go ahead and write it out one more time, 1 plus the rate to the power of time, or n, and that's just it for the future value of a single sum. So let's plug in what we know. I know the future value, 387,000. I know the present value, 300,000. I don't know my rate, so I'm going to go 1 plus r, and r is just the unknown at this time. I do know my time period, that's 5. And again, that's an exponent. So what I'm going to do is divide both sides by $300,000 to make this $300,000 cancel. I'll be left with this on a side by itself. So 300, and actually I'll type that out. 387,000 divided by 300,000 equals, and I'm just going to copy this. So 387 divided by 300 gives me 1.29. And it's equal to 1 plus r to the power of 5. Again, it would actually be pretty easy just to use basic math to solve for r, but you don't need to because you have the interest factor tables. 1.29 is the interest factor. It is the interest factor with a time of 5 and some rate that we don't know. So all I have to do is pop over to my interest factor tables. Again, I'm using the future value of a single sum one. I'm just double checking to make sure I've got the right one. I know y'all can't see the header on this window, but it does say future value of a single sum on it. So I go to time period 5 because that was the one thing of the two unknowns that are the two variables I need to find an interest factor, rate and time. I know that the time is 5. So I'm going to go across here until I find a rate that's awfully close to 1.29, and that's 5%, which actually has a interest factor that's a little bit too low, but 6% has an interest factor that's a little bit too high. So I know that the rate that I earned on that house was between 5 and 6% because the interest factor of 1.29 lies between 5 and 6%. So I'm just going to, I don't even know why it did that. So I'm just going to put between 5% and 6%. All right, now let's do the second one. So if my daughter never adds another penny to her retirement account, she should have about $1.4 million in 50 years. What I'd like to know is how much is that worth in today's purchasing power if inflation is 4% annually. So today, compared to 50 years from now, today would be the present. 50 years from now would be the future, and I know she would have 1.4 million in the future. So this 1.4 million is a future value. I'm just going to pop up here and copy this equation. This is 1.4 million. And this present value of the single sum is what I'm after. Now, I could easily use the present value of an interest factor, present value of a single sum interest factor, but I had this equation already typed, and it was handy to cut and paste. And in present value and future values of single sums, it doesn't really matter whether you use the present value or future value interest factor table. With annuities, it does matter. With single sums, it doesn't. It's just a matter of, do you multiply or do you divide? So you just have to plug in things into the right spot in this formula. So again, I'm using that future value of a single sum. That 1.4 million was my future value. I don't know my present value. That's what I'm trying to find out. I do know my rate this time. My rate is my inflation rate. That's 4%. And my N is 50. I have enough information now to pop over to the future value interest factor table and find this answer if I don't want to do it on my calculator. So I'm going to pop over to my interest factor table, future value, single sum, 50 years, 4% rate. So here's my 4%, scrolling down to 50. I see 7.1067 is my interest factor. So I'm going to just type that before I forget it, and hopefully I didn't type it wrong. So I'm actually going to copy this down now because 7.1067 is the answer to the area that I'm highlighting right now. And now because I'm after this present value of a single sum, if I divide both sides by 7.1067, that will get rid of it on the right hand side, and I'll be just left with the present value of a single sum. Oh, sorry, I was just startled. All right, so 1.4 million divided by 7.1067, I get, a very low number, 196,000 997. So you can see that in today's purchasing power, inflation hurts a lot. The 1 point, basically, you have to ask yourself, could you live off 196 if you only had about $196,000 saved for retirement? Would that be enough to last you throughout your retirement? And the answer is probably no. So, is 1.4 million going to be enough for her to survive throughout her retirement? No, probably not. Because remember, things are going to cost so much more for 50 years from now. Basically, $1.4 million in 50 years will buy the same amount of goods that $196,000 will buy today, because inflation is high at 4%, and it's growing. It's increasing prices of things for 50 years. I just double checked this answer to make sure it was absolutely correct, because I was worried. It seemed like it was a little bit low, but it is right. It's just startling how much impact inflation can have. So if you don't plan for inflation when you're saving money for a long period of time or estimating your retirement needs, you're going to make a grievous error by not considering inflation. Okay, so now let's calculate the monthly payment on a car loan. If we finance the car loan over 4 years and it has an annual rate of 12% compounded monthly. But I see I forgot to say how much the car cost. So let's say you are financing $18,000. Because car loans are typically paid monthly, and because when I go look at my present value of an ordinary annuity interest factor table, which is what I need to deal with a car loan, the lowest interest rate that I have on there is 1%. So when I make up problems that deal with monthly loans, because I only started with a 1% rate on those annuity tables, the lowest annual rate I can give you is 12%, because you always take that rate and you divide by how often interest is paid a year. Since interest is paid monthly, I have to divide whatever rate I give you by 12. Well, if I gave you a rate of 6% and you divided that by 12, that would give you an interest rate of 0.5% per month. And when you go look at your interest factor tables, I don't have fractions of rates on there. My rates start at 1%, so 0.5% isn't on that table. So I have to give you fairly high annual rates for monthly compounding. You might think that interest rates on car loans are nowhere close to 12%, and that's true if you have a good credit rating. I bought a car last year, and I asked them to provide me with the interest rates that they charge for people of different credit ratings, and I hope you can see this. They have 9 different tiers or levels of people with different credit ratings, and they progressively charge a higher rate. It's only showing up there a little bit. They'll charge you a higher rate if you borrow the money for a longer time period, although the rate doesn't jump until we switch between 60 months and 72 months, so 5 years and 6 years. If you borrow for 3, 4, or 5 years, the rates are all the same for each tier. So for tier 1, you'd pay 2.78%, whether you borrow the money for 3, 4, or 5 years. But once you hit 6 years, they're going to charge you more. But look what happens to the rate as your credit history or credit rating is so bad that it gets you to a lower tier and a lower tier and a lower tier and a lower tier, or a more risky tier is technically what this is. If your credit rating is poor, you are a greater risk to the lender, so they're going to charge you a higher rate to compensate for that risk. Look at how high the rate goes, and just in case you can't see it, a a perfect person with a perfect a good, it doesn't have to be perfect, but a nice credit score would pay a rate of about 2.78% for 3 years for a 3-year loan. That's a year. But if you had the credit score that popped you into the worst tier, your rate is 14.16%. So a 12% rate is technically possible even in today's low rate environment if your credit report or credit history is so bad that you've got a poor credit score. Hopefully you're not in that situation. So we have this problem in front of us. We have to decide, is it an annuity or a lump sum? We are trying to calculate our monthly payments. We'll have 48 months of payments. That makes it an annuity. And now we have to decide, do we use the present value or future value annuity tables? In this case, you would determine that by looking at this number. This is how much you're borrowing today, and then you're going to make payments on it in the future over the next 48 months. It's this number that determines whether you use present value or future value annuity tables. This $18,000 occurs in the present compared to when your payments will be. So I use the present value of an annuity table. So the formula is the present value of an annuity equals the payment times, gosh, that's a very long interest factor. I'm going to go ahead, I think, and write it out. I'm not sure if I actually addressed this when I was lecturing before. So it's 1 minus 1 divided by 1 plus the rate to the power of time. All of that gets done. Make sure that's an exponent. Then you take all of that and you divide it by the rate. That's the interest factor for the present value of an annuity. We're just going to look it up. So the present value of an annuity equals the payment times the present value interest factor of an annuity. And over here I'm just going to put PVIF equals present value interest factor of an annuity. So let's plug in what we know. We know the present value of the annuity, the amount we're borrowing, $18,000. What we don't know is our payment, but we do have the interest factor tables for annuities, so I can go look it up. But now I need to decide what rate am I using. So the rate that I'm going to be using, you might think it's 12%, but remember, this problem has monthly compounding. And when you've got compounding more often than once a year, you take that annual rate, divide it by however many compounding frequencies there are in a single year. There are 12 months in the year. So I'm going to take that 12% and divide by 12 months. That's going to give me a 1% rate. And then for our N, we're financing it over 4 years, but there's 12 months in the year, so we're going to be making 48 months of payments. So when I look at this interest factor, I go across to 1% down to 48 on the present value interest factor of an annuity interest factor table. I'm just going to pop this into view and hope that you can see it. It's quite small and I can't enlarge it any. But here it says the interest factor table, present value of an ordinary annuity. So you've just got to make sure you're using the right table. So we want a rate of 1%, which is the first column. I'm just going to scroll down until I find an N of 48. Oh, yay. It's on a different page. So 37.974 is the interest factor. You'd think I'd remember, but I gotta double check. 37,974. There we go. Now I want the payment. So I need to get the payment on a side by itself. I will do that by dividing both sides by 37.974. That gets payment by itself, and it will tell me the answer. So 18,000 divided by 37.974 gives me $474. Oh, almost exactly. So there is my monthly payment. So now, let's say we've saved diligently over the past 40 years and we've managed to accumulate $2.5 million in our retirement account. Now, what a lot of people do as they near retirement and enter retirement is they'll take their money that they've got invested in risky assets, and some of them will move it to very low risk assets. The nice thing about that is there's not a lot of variability in returns for those low risk assets. Unfortunately, though, there's not a lot of return. There's not a lot of high return. So that's what this person has done. They have shifted their money into, let's say, certificates of deposit. It is possible to find CDs that pay 2% a year, if you're willing to lock it in for a fair amount of time, and if you're willing to invest a decent amount of money. And so this wouldn't be an unrealistic rate to expect for CDs for them. Now, I've asked if you withdraw $100,000 a year, and I'm ignoring inflation. Inflation would make this problem a lot harder. If we're dealing with inflation and we could live off $100,000 today, well, next year if inflation's 4%, I need $104,000 to live the same way I lived the year before. That would make our math much more difficult. It wouldn't be hard to figure out in Excel, but using interest factor tables, it'd be fairly difficult, and I'm not asking y'all to deal with that. So we're ignoring inflation. How long would our retirement funds last? What a lot of people like to do is say, okay, I've got $2.5 million. I'm going to take out $100,000 a year. $2.5 million divided by $100,000 is 25 years. That's wrong. Okay, so don't work it that way. The reason it's wrong is because you're ignoring the fact that the $2.5 million is earning 2% until you withdraw your $100,000, and then you're left with $2.4 million plus interest that it earned the first year to earn interest the next year. Then you'll take out your next $100,000, and what you still have left will earn interest of 2% the next year. So you're not just withdrawing. Actually, let me say it this way. If you took the $2.5 million and you stuck it under your mattress and it didn't earn any return at all, then 25 years would be the right answer, because there would be no interest being earned. But because you're earning interest of 2% on the money you've not yet spent, your money is going to last you a bit longer than 25 years. Probably not necessarily a whole lot longer. We'll have to see. That's what we want to find out. So the big question is this an annuity or is it a lump sum? Is there anything in the problem that makes you think that we're either being paid or withdrawing a certain dollar amount? It's always the same amount and it's always the same time interval apart. If so, then it's an annuity. This is my clue that this is an annuity. I plan to take out $100,000 a year. Now, is it an ordinary annuity? Is it a future value of an annuity or a present value of an annuity? The answer to that hinges on this $2.5 million. Does this $2.5 million occur before or after the $100,000 withdrawal? You've got the $2.5 million now. You're going to make the withdrawals at some point in the future. So the $2.5 million is the present value relative to your 100,000. So I want to use the present value of an annuity formula. And I'm just going to say that's the payment times the present value interest factor of an annuity. And what we know about this annuity is it's got an I of, or a rate of 2%, and an N of, we don't know. That's what we're trying to find out. Now you need to consider, should you make any adjustments for compounding more often than once a year? Well, if this had said monthly or semi-annually or quarterly, I would have to, but since this says annually, I do not have to make adjustments. So my rate of 2% is fine. So let's plug in what we know. I know I've got an annuity that right now has a present value of $2.5 million. I know I plan to take out 100,000. And I know if I multiply 100,000 by the interest factor, I should get $2.5 million. I want to get the interest factor on a side by itself, so I'm going to take that $2.5 million, divide it by 100,000, which conveniently gives me 25. I didn't mean to write it quite like that. I meant to write it like that. And you're saying, wow, Pamela, you're doing the same thing that you just did right up here that you said was wrong. But the 25 that I get when I take $2.5 million divided by 100,000 isn't a time period, it's an interest factor. And I'm going to use that interest factor to determine the time period. So I go to my present value interest factor of an annuity file, and I go to a rate of 2%. I'm just double checking that it's the right interest factor table. So I go to 2% and I start scrolling down until I find an interest factor that's close to 25. Oh, and here's almost exactly right. So 24.99, that occurs at a time period of 35. So that will last me 35 years. Which is an entire decade longer than 25 years. So that's hopefully showing you how the interest that we're earning on that $2.5 million is again working in our favor. It's going to make our money last an extra 35 years to compared to the 25 years if it hadn't paid us any interest at all. Now this next one is a little tricky, and I did it on purpose. I want us to rework this problem. I'm going to go ahead and copy both of these. I want us to rework this, but instead of earning only 2%, I want us to earn 5%. And the question is still, how long will our money last? So we work it the same way. My present value is $2.5 million. My payment is 100,000. That gives us an interest factor of 25. So I would pop over to the interest factor table, and I would look up 25, but I don't look it up at the 2% column anymore. I use the 5% column. So I'm going to scroll down, and I'm looking for 25. I'm having to go to the next page because I haven't hit 25 yet. I'm still in the 5% column. I'm going to scroll down some more, and I'm still not running out of money. I won't keep doing this. Actually, I guess I will. I created all these interest factors on a spreadsheet. So I went out pretty far, but you can see that eventually I hit, and this is in the 5% column, I hit 20, and it never goes above 20 because something interesting is going on. I think I'll do it over here. Basically, if I've got $2.5 million and I'm earning 5% on that, I'm going to take this 5% and I'm going to multiply it by $2.5 million. I'm going to earn in the first year $25,000. That should just say first year. I don't know what I said. I'm going to earn an interest the first year of $125,000, but I'm only going to take out $100,000. So the second year, I'm actually going to start with the $2.5 million plus the $125,000 minus the $100,000 that I took out to live on. So the second year, I'm going to actually start with more money than I started with the first year. I'm going to earn 5% on it again. The second year, I'm going to earn $126,250 in interest. That's going to keep happening year after year after year. I'm spending less than I'm earning in interest. So technically, I will never run out of money. This account will just continue to grow. And when I die, it would be worth even more than $2.5 million. So this one was tricky. I will never run out of money. And I'll cut and paste that Excel file into the Word document so you've got that available when you print these out.